Hello everybody, this is Maurizio Martignano from Spazio IT Soluzioni Informatiche, a small Italian company located in Mantova, and I've been working on ISVV projects, that is independent software verification validation projects for many years, for many decades now. And in these projects, there's always applied static analysis technique to code bases written in many languages, mostly C, C++, sometimes also Ada, and most recently also code bases written in Python. With this presentation, I like to show that static analysis is always important, but for different reasons, depending on the language which is used in the code base under analysis. So we'll see that different languages have different needs. This is the agenda I'm going to follow during the presentation. First, I'll concentrate on generic static analysis, why static analysis is used. Then I'll concentrate on Ada, then I'll talk a bit about C and C++, then about Python, and at the end of the presentation I'll say some few things about the activities of Spazio IT in the area of static analysis. So why static analysis? Why static analysis is important and why it is used in verifying, analyzing the code bases in particular projects, especially in avionics, but also in the automotive industry now. There are three main reasons why static analysis is adopted. One is metrics and structure analysis. Basically, the code basis is analyzed to extract metrics like, I don't know, the number of lines of codes, the ratio between lines of code and comments, the number of lines of code inside the function, the logical complexity of the function, the cyclomatic complexity, that is kind of the number of ifs of the logical condition inside the function, and things like that. Basically, from these metrics, it's possible to compute some quality characteristics, and like the readability, the maintainability, and other characteristics. And so for a given project, it's possible to assess if that particular project has met or not its quality objective. That is, for instance, the code has to be maintainable, the code has to be readable. So analyzing the metrics is very important to perform these assessments. Another reason why static analysis is performed is to check that the code respects particular coding standards, guidelines. For instance, in the case of C and C++, in the avionics we have the MISRA guidelines, and on the contrary, in the automotive area we have the AUTOSAR guidelines. So with static analysis we can check, verify that the code adheres to those standards. The third reason why static analysis is used is bugs finding, to look issues, problems and errors in the code. From this point of view, static analysis can be seen as a sort of alternative to testing. Perhaps it's better to say that static analysis is complementary to testing, and it offers another way to find issues and problems. For some languages, like Python, when used in interpreter mode, static analysis can also be used as sort of compiler, as a compilation system to look for errors at a syntactical level, compilation problems basically. Now, already in this table we can see that in the case of Ada, static analysis is mostly used for, say, gathering metrics and making quality assessments, and also is used for checking the adherence of the code base to particular guidelines and standards. In the case of C and C++, static analysis is also used, or mostly used, for bugs finding, and in the case of Python and other interpreted languages, static analysis is used also as a sort of compiler, compilation system. Now we'll concentrate on Ada. Over the years at Spazio IT, the following static analyzers have been used: Analog Ada Control, Ada Core GNAT Tools, MATLAB Polyspace for Ada, and Shy Tools Understand. As we can see, the tools have always been used mostly for, say, metric gathering and checking the adherence of the Ada code base to particular standards. In particular, Ada Control has been used for that. GNAT metric from Ada Core and GNAT check have been used for that. And also Polyspace for Ada and Understand. Some of the other tools like Polyspace for Ada and CodePeer for Ada Core have also been used for abstract interpretation and symbolic execution to look for particular problems and, say, in general for bugs finding. But this has been a limited activity in the case for Ada. And why? Because for Ada, lots of the issues that can be found in systems written in other languages like C or C++ are preventing from happening by the language itself. For instance, many data conversion errors are prevented from happening by Ada strong typing. The compilation system, the various compiler implementation are very strict, so they take away lots of problems and lots of errors. And also in many Ada projects, testing, deep testing, thorough testing is mandatory. So a lot of problems are detected during the testing because testing is performed very well. And testing may include also the execution of runtime checks that help the developers in finding problems and issues. In 2015, Spazio IT developed for Airbus a SonarQube Ada plugin able to compute the so-called maintainability index. This according to a quality model developed, implemented by Airbus, which was very close to the ISO ISC 20010, which is system and software quality requirements, quality assessment, evaluation, and quality models. Basically, you start from the metrics like the line of code, the cyclomatic complexity, the number of nodes, and then you compute characteristics, quality characteristics like the analyzability, the changeability, the stability, the testability, and out of these major quality characteristics you can compute then the maintainability index. Now, it turned out that the computed maintainability index proved to correspond very well with the experienced actual maintainability of the actual code bases under analysis. So the computed value was a very good indicator of the quality, that is the readability and the maintainability of the system under analysis. And also the issues found by the tool identified the elements, the area inside the code base that somehow were requiring fixes and changes to improve the overall maintainability of the overall code base. This is just a picture showing the tool at work analyzing a kind of open source project. It's the library XML Ada made available by Ada Core, analyzed by the tools when it finds lots of problems in terms of cyclomatic complexity. And okay, these problems are mostly based by the fact that we have things related to characters and coding those character sets, and the code has inherently plenty of, say, logical conditions if inside it. And yeah, and this is basically the tool at work. This is the tool that was developed in 2015. Now we're moving on to C and C++, where we see that the emphasis is on bugs finding. Over the years, at Spazio IT, the following C and C++ static analyzers have been used. Gimpel PCLint first and PCLint Plus later, and then CPP Check. CPP Check is a open source CPP analyzer, and then as part of the Clang and LLVM compilation system, the Clang static analyzer and Clang Tidy, and Infer from Facebook. PCLint and CPP Check have been used mostly for, say, gathering metrics and checking the adherence of the code base to particular standards like MISRA or AutoSAR. CPP Check has also been used for bugs finding, as it's got some, pretty good tools and analysis capability quite close to abstract interpretation and symbolic execution. Abstract interpretation and symbolic execution appear, more strongly and in an effective way in analyzers like the ones of the Clang compilation system, like the Clang static analyzer and Clang Tidy, and they also appear inside the Infer static analyzer. So this is why these particular tools have been used mostly for bugs finding, and we'll see a bit about that in the next slides. Something that has to be said is that nowadays C and C++ compilers, if properly used, can be as straight as Ada compilers. So one moment that we go to full screen size. Here we have gem number 33 from Ada Core, which is classical problem with references, pointers if you like, that can be spotted at compilation time. So this is the gem, which has been just copied and made it compilable. And here we have something equivalent in C. And so what we can do very simply is to compile the thing with the Ada compiler and see that there's a problem with allocation and references to this part here is illegal, and we can see it has been spotted, so no problem whatsoever. And now we can do the same operation, the same compilation operation in C on this piece of code, and basically we can call the Clang compiler, telling to check all the things that are there and consider also the warnings as errors. So here we go. And also in the C example, the same memory problem with pointers and references been spotted, and the compilation stops. So we can use the C compiler in a way that it becomes straight and very conservative, exactly in the same way that the Ada compiler is. So going back to the main presentation, it has to be said, it has to be noticed that in some C and C++ projects, thorough deep testing is mandatory, but in some others it's not. And so the bugs finding that can be offered by that is offered by the static analysis tools could be useful, could be helpful. It has to be noted that in the Clang compilation system, the compiler and the static analyzers are based on the very same libraries. They are the same thing. So the compiler, in a way, is the static analyzer, or if you want, the static analyzer is the compiler. Also, GCC, mostly because of the competition with the Clang compilation system, is evolving dramatically, and its analysis capabilities, static analysis capabilities, are improving dramatically. The abstract interpretation and symbolic execution offered by the Clang static analyzers and by Facebook Infer are already rather powerful and are continuously evolving. So here we have an example of C and C++ static analysis applied to bugs finding, and we see a bug discovered by the Clang static analyzer. On the left we have here the user interface produced by the tool itself, by the Clang static analyzer, which is an HTML based interface, and here is how the same problem appears from within SonarQube. So there's a C and C++ plugin that gathers the data from the analysis and then displays the information about the results from within the code. And you see that also the way in which the problem is displayed from within SonarQube is pretty good, is pretty nice. Now we continue, we concentrate on Python, and we'll see that also for Python the main emphasis is on bugs finding. So over the years, to be honest, most recently, the last 2 years, Spazio IT has been starting analyzing also code bases written in Python. And for those code bases, the static analyzers that have been used are all open source, and they are Bandit, which is specifically concentrating on security issues, logical errors, and Flake 8, which is mostly on, metrics gathering, concentrating on metrics gathering and adherence, checking the adherence to guidelines and coding standards. And PyLint. PyLint has always been used also for metrics and for guidelines and standards, but mostly for bugs finding. And inside SonarQube, there's a SonarQube plugin for Python, and the plugin itself is able to do static analysis, and the static analysis performed by this plugin is pretty good, and especially in terms of bugs finding. We see a picture in the following pages. So now we are going to see the main question, that is, what is Python? Is Python a language which is interpreted or compiled? Now we are back to full screen. Here we have a very simple and stupid also Python program that basically is there to make mistakes. Basically it checks with the user if he can or not make mistakes, and if the user says yes, he'll try to use a function that doesn't exist. Otherwise it'll behave properly. Okay, so let's make it run. Okay, so let's try first like this, and then we say no, and everything is fine. But if we allow the program to make a mistake, it will say yes, then it tries to call the function prompt instead of print, and we have a problem. And this problem is detected at runtime. We're using Python in interpreter mode, so if we have some static, some syntactical errors and problems like these ones in the code base, these are only detected via execution. Now, if I take exactly the same code and I apply to a PyLint, okay, PyLint, and then you see the linter, basically the static analyzer, has found the problem and so we didn't have to execute the code. So if I apply systematically the linter to all the code base, I can extract automatically all problems and that a normal compilation activity would have found. So with the linter, in a way, I can also compile the interpreted code in a way. Just to show you, lots of web applications written in Python are based on this framework, which is called Django, and Django uses mostly the language, the Python, in interpreter mode. So all the code bases based on Django will call Python something, and then if we have in the code base a portion which has not been verified in terms of its syntactical correctness, we could have errors. If you go to Spazio IT website, there's a section where you have a pointer to a SonarCube demo always developed by Spazio IT. You go in here in the SonarCube demo, and here you have two projects written in Python. One is a Django-based CRM system, and the other is the AI machine learning library from Google, the TensorFlow, and you can explore them, and you can see how well a static analysis can also be applied to Python code bases. Here we go back to the main presentation. Just with this page we show all the steps that we followed during the demo before. So we have a very small interpreted program that gets executed also when there are, say, errors inside it. And this is a situation which is typical in very large code base, for instance web application based on Django, where say the main thing, the instruction that starts the system is this one here, where we have Python manage.py, and then this runs the server. So Python is called in interpreter mode, so we could have those issues with syntactical errors. So in case of very large code bases, linting can be used also as compiler to guarantee the syntactical correctness of the entire code base, and especially in web application, in projects where the TDD, the test-driven development paradigm is not followed, then when testing is not mandatory, having a sort of compiler checking the code could be very useful. So here we have an example of the static analysis used to look at things like metrics. So we see the complexity, or say we see problems with the coding standards and things like that. And here, on the contrary, we have an example of the SonarCube Python plugin that detected a problem. This is in the area of bugs finding, and so is displaying what is the problem and what are the statements that have been causing the problem. So this is very, very, very interesting. So some few words about the future activities about static analysis at Spazio IT. Here we have the symbols of the Clang compilation system, of the SonarCube, and of the Facebook Infer. Basically, the plans for the future activities of Spazio IT are keeping up to date with the evolution of Clang static analyzer and Clang tidy, and also to keep up with the evolution of Facebook Infer. Possibly to improve the integration of the static analyzer with a code quality platform like SonarCube. And Spazio IT has developed a thing called Safe Toolset, which is basically a virtual machine containing SonarCube, the code quality platform, and a set of static analyzers. And at the moment, this container has static analyzers for C, C++, and for Java, and Spazio IT intends to add also support for Python to this particular box, this particular container. So these will be the major activities for the next few months and years, I guess. Here we have an example of the current, that is April 2021, integration between the Clang static analyzer and SonarQube. You'll see that this is the HTML-based user interface of Clang, and here you have SonarQube. They are pretty similar, they are pretty good, and having SonarQube that displays not only the Clang found issues but also other problems, other things. So you have SonarQube, which is a single platform where you see all the problems, all the errors. You see the problems coming from the static analysis, but also you see the problem coming from testing, from coverage. So you have a single point where you can basically associate the issues with the lines of code that cause those issues. So this is pretty good. The same level of integration at the moment, which is again April 2021, is not available for Facebook Infer. For instance, here we have a particular issue where in the user interface on the left of Infer, we have the stack of reasons that cause the issue, and on SonarQube at the moment we only have a pointer to the particular location of the issue without seeing the causes that somehow produce the appearance of that issues, while for the Clang static analyzers in both interfaces we see what are the causes. We can also see that somehow at the moment the user interface of Facebook Infer is not as nice and as well readable as the ones from the Clang compilation system. And that's it. Thank you to all of you for having listened to me. Talking to an audience which doesn't exist, or a virtual audience, is very difficult and makes, I'm pretty sure, my talk and my narrative a bit boring and with some kind of soporific effects. So if you have resisted to my terrible treatment in terms of making all of you sleeping, again, thank you very much for your time.